This is an introduction to curve fitting in Python. First thing we need to do is import the relevant boilerplate. So we have numpy, matplotlib, and then from previous discussions we have quad, fsolve, interp1d, and now the new one is from scipy.optimize import curve_fit. So curve fitting is used to represent a set of data by a model function. The model function can be a form meant for convenience. That is, we might want to fit, we just need an equation that we can use to represent the data succinctly. Or there might be an underlying physical process that we're trying to apply to the data. So we have a model, a physical model, and we might be trying to find best fit parameters. So an example of that might be kinetic data where we measure a rate versus a temperature, and we want to find our pre-exponential factor and an activation coefficient, activation energy, for example. So in Excel, we used a trend line. So we had a series of XY data, and we plotted them, and then we right-clicked on the plot, and then add trend line, and then we can select a trend line type, whether it be polynomial, linear, power law, etc. And we clicked a button to show the equation on the plot. We could right-click the equation and format it to change the numerical output. If the data that we have in Excel, if the model form isn't available, we can either massage our data to get it in the right form, such as by taking the log of both sides and then plotting changed variables, taking 1 over both sides, etc. Or we could we could make a few cells that have the parameters of a generic function, and then we have our XY data, and then we write a formula for the modeled Y values. We take the difference between the given Y values and the modeled Y values. That's the error, and then we compute the sum square error by using the sumSQ function, and then we use the solver to minimize the sumSQ, the sum square error, by changing the 3 or 4 or however many parameters we have. So that's the approach that we used in Excel, and even though the approach is different in Python, all the parts are still there. So we're still going to have a series of X and Y data, and then we're going to use different functions in order to find those parameters. So there's 2 major methods that we'll use in Python. The first is called Polyfit, and that's used for fitting polynomial functions. And the second is called curve fit, and we'll use that for more general curve fits. So you'll use Polyfit if you're fitting a polynomial. It's best to use the best tool for the job, and Polyfit is optimized for fitting polynomials. For everything else, you can use curve fit. So let's first look at polynomial fits. The syntax it comes from numpy, so it's np.polyfit. There's 2 functions we use, polyfit and polyval. Polyfit takes the X data, G for given, and the Y given data, and then the order of the polynomial we're using. So a straight line would have order 1, quadratic order 2, cubic order 3, etc. So those 3 things, the X data, the Y data, and the polynomial order. And then it returns an array of polynomial coefficients, starting with the highest power of X. Once we have these coefficients, we could write a function, if we wanted to, like def poly, that then returns a polynomial and evaluated it whatever we want. But NumPy has provided that for us with a function called polyval, where you give it the polynomial coefficients and the point you want, and it evaluates the polynomial at this point. And this can take a single value or an array of values. So let's go ahead and try this out. We're given some data, xg, yg. So this might be computed by yourself, or you might have gotten it somewhere. We'll take it as given. And then the first thing to do is get the polynomial coefficients, np.polyfit, xg, yg, and the order of the polynomial. We'll do 3. And then we can evaluate that polynomial anywhere we want. So we could do xx. Let's make a whole bunch of points equals np.lens space. We'll go from 0 to 5 with, I don't know, 1,000 points. And then yy equals np.polyval. Give it the polynomial coefficients we just fit and the x values we want to evaluate it at, xx. And now we can plot plt.plot xg, yg, and we'll plot that with symbols. And let's also plot the xx data and the yy data as a line. And we'll crash because we didn't import our libraries yet. Let's go ahead and do that real quick. Run this cell. Okay. And we get the polynomial fit through the data, third order polynomial. So that's how that works. Polyfit and then polyval. And if you like, you could, again, if we wanted to, we could do def poly define a function where we pass in the polynomial coefficients and the x data we're interested in, and then we could do return p0 times x cubed plus p1 times x plus p2 times x plus p3. And let's try that as well. We'll do xx and poly xx, turn that off, and we get, oops, missing it. We need to pass in a p here, and we get the same thing. So this is effectively what polyval does, but we don't have to hard code it. Okay, so there's basic usage of polyfit and polyval. Let's go ahead and do this for another exercise where the data go from 2 to 8, but let's plot the results. Let's evaluate the polynomial and plot the results on a wider range to see what we get. So again, pause the video and go through and do this yourself to get practice. Try to remember what the names of the functions are and what to call them with. Okay, so we do p equals np.polyfit xg, yg, and a sixth order polynomial. And then we can do xx as np.lens space. We'll go from 0 to 12 with 1,000 points. And yy is np.polyval. P and xx. plt.plot xg, yg. And we'll do xx and yy with a line. And we get this function. Not a very nice looking function. So the issue here is that when we plot on that range, polynomials by definition go off to plus or minus infinity as you go to high or low values of x. And so we can see that here. So we're going to get a nice fit in the data, but outside the range, it's anybody's guess. So let's go ahead and zoom in on this. plt.x, well, just do ylen. Maybe -2 to 3 or something like that. And you can see that the data fit, maybe 4, oops, 4. The data themselves just go 1, 2, 1, 2, 1, 2, 1. So it's unlikely that a sixth order polynomial is ideal for this, but we only have 1, 2, 3, 4, 5, 6, 7 points. So if you have 7 data points, then a sixth order polynomial is as high as you can go without the problem being singular. And for a sixth order polynomial with 7 points, you get the polynomial will actually go perfectly through every one of the points. But that doesn't necessarily mean that the polynomial is a good fit to the data. As you can see, in between the data, you often get behavior that's not exactly what you would expect from the form of the data. So that's one thing. And the other is outside of the range, polynomials are going to have really scary behavior. So the two take-home messages are: try not to fit too high an order polynomial to the data unless the data is pretty smooth. And you've got and normally you'll have more data points than the order of the polynomial. And second, be really cautious going outside of the bounds of the original data when using a polynomial fit. Okay, so let's go ahead and do a general curve fit. So those are the two things tell us about, be careful about outside and between the data. Okay, let's look at a generic curve fit. If we have a general function, f of x, that depends on parameters a, b, and c, and we want to find the values of a, b, and c that are optimal as per least squares, in a least squares sense, we use the curve fit function for that. So from scipy.optimize, import curve fit, and then the function call is as given here. So curve fit, you pass it the name of the function you're fitting, the given x data, the given y data, and it returns two things: an array of the parameters that you want, so in this case a, b, c, and extra information. So you can look at the help for curve fit to see what this extra is. So it's basically returning a tuple of these things: parameters and extra information. So the curve fit function is going to expect, when it calls your function, it's going to be calling it in the form f of x with parameters a, b, and c. So when you define your function, you'll want to go def f of x, comma a, comma b, comma c, etc. for however many parameters you have. You might have 1 or you might have 10. Okay, so let's go ahead and do an example of this. So we have a function a e to the minus bx plus c, and we have some data that are given here. In this case, we have a whole bunch of points. Let's go ahead and plot them right off the bat. plt.plot xg, yg, and we'll do dots with marker size equals 0.1 so that we can see the plot really nicely. So essentially we used this functional form, and then we added some normally distributed random noise on that. So you can see that at any given location, you've got a higher density along the middle of the cloud, and then it kind of tails off towards the edges. Okay, and then let's do the curve fit. So first thing to do is define the function def f of x, a, b, c, like so. Add a little space there just to highlight it. And then return a times np.exp of minus b times x plus c. And then we'll curve fit it, params, comma, extras equals curve fit. Give it the function name. You can name this anything you want. I use f here. And xg and yg. Now that we have the parameters, we can recover our ABC if we want. So ABC equals params. And it works. And then let's go ahead and plot the data using the same xg. We have a lot of xg points, so we'll just reuse those. So we'll go we'll do plt.plot xg, and then we'll use the function f of xg abc, and we'll do a dash straight, a line through those, maybe line width equals 4, and we can see the curve fit, very nice, right through the data like we expect. Okay, so the second part, so the first part we define the function, then we get the curve fit, gives us our parameters. That's an array of parameters, and or a tuple of parameters. In this case we have, let's double check that, so type params nd array, so we're able to expand that here. And then we have the a, b, and c values of these parameters. So you could do this, or you could go a equals params 0, b, c, like so, to recover the parameters. Or you could just not do any of that and just go f of xg params 0, params 1, params 2. All of those are just fine. So recovering the parameters for convenience of presentation, a, b, c, and we're calling the function with those optimal parameters, and that gives us our orange line here. So that's curve fitting in a nutshell. So the thing that's missing from this is there's no guess. We don't have to provide curve fit with a guess. It'll find its own guesses and give the optimal parameters. If it has trouble with it, you can always provide a guess. Just do help curve fit, and let's go ahead and do that. So help Whoops, turn that back on. Help curve fit. And you can see P0, you can give it those parameters, and there's other options provided there. So if we, if you want, you could give it P0 equals, and then A guess, B guess, C guess, where you specify what those are. Okay, and that is the basics of curve fitting using Python. Okay. So there's also least squares approximation, and you can go through this in the notes. It's a more hands-on approach for understanding how these curve fits work, and I'll just go through them briefly. So you can define a curve fit in lots of ways, but the most popular is probably to look at the sum of the square error. So if we have a function like ax squared plus bx plus c, then we have a set of points xi, yi that are given to us, and then we have a set of modeled points xi and the corresponding function evaluated at each x using a, b, and c. So we'll call this fi, and then we can find the error as the difference between the modeled y and the provided y, and we can then find the sum of the square error, like so, and that's just the sum of the square error, so the function evaluated at the point minus the given point, that squared, and then you sum that over all the points, and this error will depend on your values of a, b, and c, so it's a function of a, b, and c, and we want to minimize that error with respect to a, b, and c. So we remember from calculus that the error will be minimum when the partial derivatives with respect to a and b and c are all equal to 0. And so if we evaluate the derivative of e with respect to a and b and c, we get the sum of 2 times this quantity times the derivative of this with respect to a, which in this case is x squared. And when we do it with respect to b, it's x, and when we do it with respect to c, it's 1. Now we have 3 equations and 3 unknowns, a, b, and c, and we can feed those to a solver. In this case, the equations are linear, so we could use a linear solver, or if they're nonlinear in a, b, and c, then we can use a nonlinear solver like fsolve. And we define the function and then feed that to fsolve, or make an ax equals b matrix out of it, and solve for the array of coefficients a, b, and c. And that's it. So that's basically how you would do that. So here's an example. Ax to the b, the error would be ax to the b minus yi squared. You get 2 times this. There's the derivative with respect to a, and there's the derivative with respect to b. And so you have 2 nonlinear equations and 2 unknowns. And you can then solve those directly using a nonlinear solver, or you could change variables first by linearizing, and the details are given here. You basically take the log of both sides and then work in log a as your variable, which we call a hat instead of a itself. And then we have a hat, b, and y, and then this formula is linear in a hat and b, and so we solve for a hat and b, and then once you have a hat, you can recover a from exp a hat. So that's how you would go about doing this in general. Okay, so that's a brief intro to using curve fitting in Python.